This video shows typical continuous soil moisture monitoring data from a capacitance soil moisture probe and briefly describes some considerations in the interpretation of the data. The data shown here come from an AquaCheck capacitance soil moisture probe with sensors configured to read relative soil moisture at 4, 8, 16, 24, 32, and 40 inches below the surface. Time is shown on the x-axis. Relative soil moisture is displayed on the y-axis. This graph shows each sensor according to the relative soil moisture value. Coincidentally, they line up from shallow to deep, but this is not always the case. The undulations observed here at the more shallow sensor depths are due to daily temperature fluctuations. Deeper sensors tend not to show the undulating effect because soil temperature remains stable. Research has shown the temperature effect on capacitance readings is frequently less than 2% of volumetric water content. The average trend line is what is important to observe. This sharp increase in relative soil moisture signifies an irrigation or precipitation event. If moisture advances to the deeper depths, you will also observe an increase, but the relative change tends to be less because soil moisture distributes more slowly during unsaturated flow. Following the end of an irrigation event, there is a period of free drainage where the saturated surface soil returns to an unsaturated condition. This next graph shows the same data but in a slightly different format. Now the sensors are stacked on individual y-axes in shallow to deep depths. This allows you to more intuitively observe trends as they occur below the surface. Soil moisture depletes through the process of evaporation from the surface as well as transpiration through plant uptake. In the active root zone, these changes in relative soil moisture are easy to observe. The steeper the drop, the more the depletion of soil moisture. Soil moisture at the surface initially will have a very rapid decline as evaporation is quite active, followed by a slower decline as the evaporative processes slow down. Transient flow or redistribution of soil moisture may occur depending on the gradient as moisture moves from areas of wet to areas of dry. If we zoom in to the irrigation event, we can make some additional observations. First, we can observe the advance of the wetting front, which in this instance registered at the 4-inch depth at approximately 2 p.m., followed by the 8-inch depth at about 4 p.m., and concluding with the advancing moisture reaching the 40-inch depth approximately 12 hours after the beginning of the irrigation event. By definition, field capacity is defined as the amount of water a soil will hold after it has been saturated and allowed to drain for 24 hours. By observing the irrigation event and the beginning of free drainage, we can estimate field capacity approximately 24 hours later. This works reasonably well with surface sensors but may not hold true with the deeper sensors since we are unsure whether the soil was ever fully saturated before free drainage began to occur. We're going to fast forward a bit to later in the season, where we observe an irrigation or precipitation event that was short in duration and did not indicate moisture reaching the 16-inch sensor depth. Further, we can observe that by lengthening the time between moisture events, our crop can deplete moisture from all depths. Finally, we observe another short duration moisture event that in this case is likely from precipitation that only showed wetting advancing beyond the 4-inch depth and maybe just slightly reaching the 8-inch sensor depth. We will conclude shortly but want to show another way of displaying soil moisture data. In this graph we have averaged the readings of the 6 sensor depths to give us a summary display of the average soil moisture profile from 0 to 40 inches. If the active root zone of the crop extends to 40 inches, then this picture more fully represents the average soil moisture conditions the crop experiences. When the irrigations are relatively frequent and the soil moisture profile is already near capacity, then relative soil moisture for the profile will change very little. Reducing the frequency of irrigation or shortening the duration of irrigation will allow you to utilize the soil moisture already available. Continuing to irrigate more frequently than needed or running the set length for extended periods of time can lead to increasing relative soil moisture. Lengthening the irrigation frequency allows the crop to draw from existing soil moisture reserves. The pattern we often look for when setting thresholds for a refill point is this idolized pattern, where we see an initial rapid decline followed by an ever-flattening slope. As the line continues to flatten, it is an indication that soil moisture is changing more slowly throughout the profile. The key is to identify the declining soil moisture level you do not desire to drop below, and then set the thresholds accordingly. Monitoring both the frequency as well as the set length will allow you to manage soil moisture more carefully. A capacitance soil moisture probe giving continuous readings over time is a great tool, but must also be complemented by periodic in-field monitoring. We hope you have found this video helpful. If you have further questions, we invite you to inquire at your local Helena Chemical Company location. For a list of locations, please go to www.helenachemical.com. Thank you.